Thanks, Chris. It's a pleasure to be here. I am particularly appreciative of the opportunity. It's actually been quite a stimulating day so far, and when you're the second to last speaker, you have the benefit of being able to just say, well, that's been said before, and that in several places I'll buy a little bit of time because it has been said before. See, why is that so dark? It's a lot darker than I was expecting it to be. Right. Oh, that's much better. Anyway, I also need to express some appreciation to sponsors that made this work possible over about 3 decades. And this is sort of an enterprise that uses a model called the Global Change Assessment Model, or GCAM. And it's grown to the point where it's not just me anymore. It's me and a relatively large and a very talented team, many of whom came from Stanford. We have a little Stanford mafia. I'll begin by going to the motivation for this research. This research into negative emissions comes out of things that I was doing, in fact, with Chris. And as we were developing the foundations for the 5th assessment report, the question arose, what's the range of radiative forcing that should be used by the climate modeling community? And Detlef Van Buren had done some back-of-the-envelope calculations saying you could get to 2.6, which is equivalent to 450 ppm CO2 equivalent in the atmosphere at the end of the century. But he hadn't actually ever run it through a model, so he hadn't dotted his I's and crossed his T's. And so that became a cause celeb. But a couple of groups went out and said, let's see if we can do it, run it through models and actually develop it. And they did, but you'll note that the way these models got to 2.6, which is, again, about a 50-50 chance of staying at 2 degrees or below throughout this century. The way they did it was with bioenergy and CCS that in some instances was about as big net negative emissions as the world has positive emissions today. And that's pretty substantial. It also piques your interest. The other thing that piqued my interest was that I was always having these problems when we would break out regions. We would have regions that in some of the more stringent scenarios would go negative, but we didn't have bioenergy and CCS in our model. What we had was bioenergy, and we had gas units that could burn could burn natural gas, and the model had a gasification process which could take bioenergy, turn it into a gas, put it into a pipeline, and it was not accounting. It was, in fact, the model was busily going to negative emissions. There are a lot of pathways to negative emissions, and I think it makes it a really interesting process. Not just growing bioenergy and using CO2 capture and storage, but you actually have options that have been discussed here as well, and you can use it as a feedstock for long-lived materials such as plastics, and the model has discovered that it could do that too. And I think all of this makes this a really, really interesting topic. Now, I'm going to confess that although every large point source can use CO2 capture technology. There's a technology available for it. We don't put any CO2 into the oceans, and we don't have an explicit technology for biochar, and we don't do free air scrubbing in this. But as several of the other presenters have pointed out, this technology and its components, but also the technology in combination is in existence. The one thing that has hardly been mentioned at all is that no board of any utility is going to approve deployment of scrubbers onto their fleet of power plants if the price of carbon is 0. that's something that's probably an important thing to point out. So we're going to explore worlds in which the price of carbon is not zero, and in some cases substantially not zero. The other thing that turns out to be pretty darn important is the institutional framework that facilitate this business model to actually operate. And the policy environment also turns out to be very substantially important. And I only have time to run through one variant, but I could run through another variant that had a completely different outcome. So I'm going to explore two questions. One, is it technically possible to limit radiative forcing to 2.6 watts per meter squared, or 450 ppm CO2 equivalent in the atmosphere, the same thing? Is it technically feasible? I'm not going to consider political or economic feasibility. I'll show you what the economics looks like, but maybe it's a bargain, maybe it's too much to produce. And then the other question is, do resource limits preclude successful deployment? Is there enough storage capacity for all the CO2 that gets captured in scenarios that are trying to go down to 2.6? When you do that, is there enough CO2 storage capacity in geologic repositories? Is the constraint on land and food, is that a showstopper? And that's why you use a model like GCAM. The GCAM model is an integrated assessment model. It's where you try to put all the pieces of the puzzle together. GCAM is an open source model, and so the good news today is, even if you think that every assumption that I tell you I made is absolutely ridiculously wrong, you can go get the model. We'll ship it to you. We'll ship you the source code, and you can actually do it right. And so all you have to do is send me an email, and my email address is jae@pnnl.gov, not .com, .gov. It's a dynamic recursive model. It's a fully coupled model. And I think that's an important thing to point out, that it's not soft coupled between land use and the energy system and the economy. It's hard coupled. Everything talks to everything else. You can't solve the land markets without solving the energy market. It's all interconnected, and it's fully integrated. And that actually plays out in some really important ways, since the amount of land is finite, and if you want to create a market for bioenergy, which turns out to be the largest single thing that's going on the planet in a 2.6 scenario, the land's got to come from someplace, and demand curves for food are pretty darn inelastic in the GCAM model, and I think a lot of people are hard over about eating. So the model it has to reconcile that, and it reconciles it in a really interesting way. The short answer to is there how much CO2 geologic storage capacity is there's quite a bit. This is what's called practical potential geologic storage capacity. It's about 7,000 billion tons. There's a larger definition, which is effective capacity, which is about 27,000 billion tons of CO2. And I'm very tightly constrained, which is called a match capacity, where you actually have to have a source and a sink that's been verified that match together, which is significantly smaller. It's only about 400. The obvious thing to point out is that the story is all about deep saline reservoirs onshore and offshore. The regional distribution of the practical geologic storage potential is really interesting. From the last time I made a presentation about this to this time, things have changed dramatically. Latin America was like no place on this map. Turns out the Amazon basin is undergirded by CO2 reservoir capacity. China's reservoir capacity has been shown to be, it's a supergiant. The US, we've always had large, but that 7,000 billion tons, as you can see, is not distributed equally around the planet. You can see you got China, which is the supergiant. You've got depleted oil and gas reservoirs in the former Soviet Union. I suspect that when we start looking more closely at the former Soviet Union, it's going to be a lot bigger, but you've got a lot of deep saline reservoirs in Latin America. You've got places like Japan and Korea, which are the have-nots of geologic storage, but even there, it's non-trivial. The experimental design that we have, we're going to look at two different kinds of worlds. One is an idealized world. This is what most of the literature that you read is all about. All the regions initially begin mitigating simultaneously. They have a price of carbon that everybody looks at. It's all the same. This is Chris's point from this morning. That price of carbon rises at an economically efficient rate called the Hotelling PEC-1 rate, which is the rate of interest plus the removal of CO2 from the atmosphere by the oceans. The other is a delayed accession case in which we say, well, not everybody's going to start off at the same time. Western Europe, Eastern Europe, and Japan start off in 2015. Then later, the US comes in, as does Korea, China, Canada, Australia, New Zealand. In a third tranche, India, Latin America, other regions. And then finally, Africa, former Soviet Union, and Eastern Europe come in the final period. There's another analysis which we do in which we say, suppose that two regions never come in. That's going to be interesting. So the technology regimes, we look at a reference technology, which you have bioenergy, you've got CCS, you have nuclear power, you've got all the other technologies. Then we run one with CCS off, run a same set of scenarios with no bioenergy but CCS available. Then one with no bioenergy, no CCS, and finally what we call a low-tech case, which is no bioenergy, no CCS, and no nukes. And the question is, can you do 2.6? And can you do it three ways? Can you do it if everybody starts at once, if you have delayed accession, and if some of the parties don't come in? So the feasibility. The first point, the idealized, it worked. As I think David Keith was saying, when you know it's coming, you actually, and you know you've got that technology to draw down fast, the carbon prices are initially low, emissions mitigation is delayed. Since the goal was stated in terms of getting to 2.6 at the end of the century, you get these overshoots. As you pull technologies out, it becomes more expensive. Emissions mitigation gets shifted toward the present rather than the future. The overshoots are reduced. Now, as you pull countries out and have delayed participation, but eventually everybody comes in, you get a really interesting set of differential cases. One is you get a wiggly radiative forcing path, even though you've got a smooth and economically efficient price path. That has to do with the policy interactions between countries that are participating and the way they treat land. If you're in, you value carbon. If you're out, you don't. If you're not mitigating, you put a zero value on all carbon. Because the world is connected by international trade, countries that value carbon want to store carbon on their land. They actually invest in forests as well as bio-CCS. But the countries that don't will sell food cheap, and so you get this deforestation to make way for afforestation, and those two don't balance because you blow off trees 50 to 100 years of carbon accumulation to buy the next 5 years of carbon accumulation. So you're getting much bigger overshoots because it takes a long time to get enough traction so you can draw that down. Bioenergy CCS gives you the largest overshoot. Again, the weaker the technology suite, the more mitigation you do, and the earlier. If you didn't have the former Soviet Union and the Mideast ever come into the regime, we broke the model. There was no way that the GCAM model could, take into account the fact that a lot of these regions weren't coming in until 2070 anyway, so you had the staggered accession. But when two of them were out, you couldn't draw down that carbon overhead from the late arrivers and plus the ones that just never are ever going to come in because they're doing all the wrong things. how much did this thing cost? Well, here's the carbon price. And you can see that the carbon prices are, rise fairly steeply. They get up over $500 a ton in the reference scenario. It's about 4 times more in this idealized world where everybody's on board. But when you get the delay and you start pulling technologies, the first thing you notice is that delay, if you've got the full technology suite and you can drive those emissions deeply negative at the end of the century, the cost penalty's not that bad. If you start pulling technologies out like bioenergy or CCS and say, I'm not going to do one of those, yes, you can get there. You saw that you actually solved, but the prices that you see are just, well, you got to break the chart because you're basically 3 orders of magnitude up. So that's pretty interesting. The fossil fuel path, since I'm down to my final 4 minutes, the obvious that the more technology you have, the deeper you can dive later. The deeper you do dive, as you pull the technologies, the fossil fuel and industrial emissions are drift down in the near term and up in the long term. Delay shifts the whole thing. You get higher emissions near term and lower emissions long term. Land use is much more interesting. Land use, as soon as you value carbon, and again, I'm valuing all the carbon on the planet, that is, if you own a stock of carbon, you receive a rent payment for holding that stock. If you increase the stock of carbon in this, this model calculation, if you increase your stock of carbon, you get a bigger rent payment. If you deforest and you reduce the stock of carbon, your rent payment goes down. It's that simple. It's simple economics, but it drives, because there are 2,000, as several people point out, there's 2,000 billion tons of carbon in terrestrial systems, about 2/3 of it in the soils, because almost any price on carbon means that it's an enormous value. And you just run the calculation at $100 a ton. It's basically the US GDP that you're holding. That's the value of the stock. Then what happens when you delay? What happens when you delay is you get these interconnections, deforestations. That's these spikes in deforestation. As you have non-participants and participants, this carbon leakage is a really big deal. It's only when everybody is finally in that at the end of the century that you finally begin to go, you eventually go negative. Carbon storage, so here's the carbon, the storage in geologic formations versus the maximum potential. You can see that it's well inside. And in fact, one of the things that's interesting is, well, I haven't got time to go into that. If I look at the carbon accumulating on land, I think what's really fascinating is how big these numbers are. That the amount that you can store on land is really big. It's much smaller in the delayed scenarios because of that interaction with non-participating regions doing deforesting, and you don't recover it all. But when you stack it all up at the same time, green is terrestrial carbon storage. This orange is the storage in geologic formations. What I was impressed with, and I guess learned all over again, is that these numbers are big, and you can get to negative carbon emissions for the planet if you only are storing carbon in forests. So I think that's really one of the major lessons. Just summing up, so the answer to the technical question was yes, as long as you got everybody in. You can do it with a wide range of technology regimes, and you can pull technologies which you would think are absolutely essential, and you can still get there, but the price is just, you have to break the graph to get the costs up there. The lowest costs are always with the bio-CCS in there. Delays in the mitigation interact with the cost and the technology in very nonlinear ways. You can think, either one is not that bad, but the combination can be just absolutely devastating. And neither the limits to geologic storage availability nor land are meaningful constraints, although I will add, at the expense of running over my time just a shade, I will add that to get land for both new forests and bioenergy with CCS, something had to give. And since demand curves for food are highly inelastic, but people are willing to shift within foods, what happened was you moved from high carbon intensive diets, not because you thought it was the right thing to do, but when you showed up at the market, the prices were torqued in a way that moved the diets of the population over toward low carbon options. So I'll leave those sort of the major findings up, and if you have any questions, I'll be happy to try to answer. Yeah. Yeah.
I know this is a perhaps strange question, but you say that BECCS will save money. How much money during 1 century, for example, this century?
Well, just go back to the...
Is it trillions or billions?
Yeah, I didn't actually run the total cost because I didn't have time to do it before the session. But if you can think of this as an index, this is probably about 2% of global GDP over the century. So if you use that as a benchmark, and everything should scale to this. Everything should roughly scale. So you're talking about very large numbers in terms of how much having bioenergy and CCS, having that combination if particularly in the delayed scenario, having bioenergy and CCS both meant that the delay, yeah, it was expensive, it cost, and the biggest cost, of course, was the fact that you overshot by more because you had these people, these parts of the world that were actually not only, they weren't just delaying, they were actually increasing their emissions as a consequence. And so it allowed the cost to be much lower. As soon as you pulled that out and began to pull these things, the costs just go through the ceiling. Yeah. Well, you should handle this. It's your
go ahead. You pick.
Why don't you take numbers?
Ahead, and then.
Yeah.
Does your model include tariffs of any system to prevent carbon leakage?
There are, you can turn tariffs on in the model. Tariffs were not turned on in the model. There were no border adjustments in these runs. We could do that. And in fact, there are all kinds of different policy regimes that you can begin to explore. This is just the tip of the iceberg.
Thank you. I have 2 comments. One deals exactly with your presentation. Is that you say about delayed activities from some countries, or maybe some will stay out of the problem. I believe that this present economic crisis can give us an idea how hard it is for some developing countries to accept mitigation efforts. You see countries, rich countries, they are postponing any activity on environment because of the economic crisis. And some of these developing countries, they are in economic crisis for centuries. So you can make understand why it's so difficult. The second point is an ethical problem. We have, does not deal only with your presentation, but with everything that is occurring here. We tried to convince policymakers that the door for 2 degrees C was closing. And now we come and say, look, guys, we have another solution. So really, are we helping society to solve the problem, or we are just creating another opportunity for policymakers don't do nothing?
Well, 2 things. One is, I totally agree that as long as the price of carbon is 0, this is all just good computer fun. And secondly, you just got to, you have to lay it out the way it is. If the political process doesn't work out well, I'll be frustrated too.
Both of those are great comments for the discussion section, which will follow one more talk. quick time for one more question, if there is one. Dominic?
Hi. Yeah, the very high carbon prices you've got there are pretty much driven by the fact that you've decided on what your cap of emissions are going to be by the end of this century, and you're looking at what the price will be required to actually reach that target. How realistic do you actually believe that people will pay that price rather than decide at the end of the century, God, that's a lot of money, we'll just adapt? Those that can will adapt, and those that can't will die. well,
I mean, that's why you run the model, is to get some information. But the model, that's not what the model is built to do. The model is built to shed light on an issue. You could run it, and if you know what the maximum price that politicians are willing to pay, you can put that in there, and you can see what you get, and then you can run the damages.
Quite interesting to actually put in cost of adaptation measures in as well, and then see which might be favoured.
Yes, and there's a working group on that.
Got it. Okay, thanks very much, Jay.